Uh, okay, so you guys are filing in little by little. That's cool. Whenever you have a question or something pops in your head, by all means, just blurt it out or yell at me. I don't mind any interruptions. The chat feature I don't use too much, but like I said, just interrupt and yell. I would prefer that instead. All right. So what I'm going to do, the first thing is to share my screen. And you should see this screen in front of you now. This is pretty much the content when you log into Canvas. So do you guys see that?
Yeah, we see it.
Okay, awesome. So I'll just click the student view. And so this is more similar to what you're gonna see. This is our syllabus and schedule right here. This is where I'm gonna put the recorded Zoom lectures for the first 4 meetings. So you click in there and I'll have links, hot links to the videos for each one of these meetings. So today's meeting will go in here once we're done. All righty. So back to the home page, we have our syllabus, which we'll go through in a second. Here I have some back test examples. So for this course, you, as part of your grade, you're gonna wanna do the homework assignments because that's gonna prepare you for the tests. Now, what are the test formats? The test formats are gonna be ones where you come to lecture in person and I hand out an exam, which is roughly 4 pages of problems. And you can look at, like, the first exam is gonna look similar to this back exam, which was given in spring of 2019. So you can download these, print them out, and try them. And they essentially look like this guy. So exam 1 is gonna have as its topics kinetics and equilibrium.
Wait, do we turn these ones in?
Yeah, this is going to be, no, these are practice. So these ones you just look at, it kind of gives you a flavor for what yours is going to look like. So this exam was given in the spring of 2019. And so I handed this out to my class. And so I'm going to hand one out to you guys. It's going to be similar in spirit, but of course it's going to have different problems. So you, the reason why I posted these is to give you an opportunity to print them out and put yourself in test situations and practice your exams. So you can get your stopwatch out and say, okay, on your marks, set, go, press the stop watch button, and then in an hour and a half, press it again and stop. So you want to be able to finish this exam in an hour and a half. And it's about 4 pages, and there's all the problems with the points outlined and so forth. So after the next 3 weeks, we will have gone through material that would allow you to complete an exam up to this level. Okay.
Hi, Professor, I have a question.
Yeah, shoot.
Can we bring our notes to the exam?
Great question. The answer to that question is no. You can't bring your notes, but you will be allowed a 3x5 card. So that's 3 inches by 5 inches. So they're, you know, the standard index cards where you can put anything you want on it, front and back. So it'll be like a cheat sheet. and you can use anything on that 3x5 card. The reason why I don't want you to have your notes and your textbook and everything else out is because it gives you a false sense of security. And some students might think they can learn the material to answer a question like this during the exam, and you can't. It's a waste of time to have all that material. A 3x5 card where you just need to look up an equation or a definition or a unit conversion or something like that, then sure, you can do that. But there's no way you're going to learn enough material to answer a question like this. And I don't want you just to copy random stuff out of a textbook and to think you're going to get credit for it. So to be prepared for the exam, what I suggest is that you study the notes, you do the homework and understand the homework. And then after we get through all that, you ask questions during our meeting periods, and we'll have a bunch in person before this exam, because we're only meeting for the first 2 weeks, and this exam is not scheduled until the 5th week of instruction. So we'll have ample opportunity to get together in person and for you to hash out any problems you have with the material, and we can go over it in lecture. And that way you'll be prepared. So you need to do your homework and understand that ahead of time, and we'll go over any problems you have with that. You need to review your notes and the things that we talk about in our discussion meetings or lectures, whatever you want to call them. And in doing the homework and talking about the material, this should give you an idea for what you might want to put on that 3x5 card. And then you can sit down and, like I was saying, do a test run through an exam, namely one of these back exams. And this will further help you maybe write out your 3x5 card that you want to bring to the exam. So that's a long-winded answer, no and yes. You can bring the 3x5 card, but nothing else. It's just a pencil, calculator, and an eraser. I think that's all you'll need. Does that answer your question?
Yes, thank you.
Sure. Okay, so you have an example for each one of the 3 exams that you're going to have. This is exam 1. It was taken from the spring of 2019. This exam 2 was taken from the fall of 2015, and exam 3 here was taken from the summer of 2015. So you have your 3 examples. Here, of course, this is where you get access to what we're doing now. So I assume you found that. Down here is the PowerPoint notes, which we're going to use to talk about the concepts. So it's kind of a springboard into our discussion. We'll look at those notes and we'll work through the concepts. And this is a good spot for you to ask questions. So when we get together in our discussion format, either in Zoom or face-to-face, we'll be going over these notes. And it's kinetics. We're going to start with chapter 12 in the textbook. Now, there's a homework that's connected with each one of the chapters that we do. So here's the homework for kinetics. The next chapter is equilibrium. There's the homework. The next one's acid-base, chapter 14, homework, and so forth. Now, these homeworks are multiple choice. They're all in Canvas. And you get the best of 2 takes at doing the homework. So you can click here and it'll say take the quiz. The due dates are artificial and they're set in your schedule. And we'll go over the schedule in a second from the syllabus. Now, those artificial due dates that are set in the schedule are just to help you stay in pace with the exam and make sure that you're ready for the exam when it comes up. So try to hit those due dates. Anyway, the quiz looks like this. So it's called a quiz or a homework. Canvas calls it a quiz. It's really just homework. And so you have these problems, and these problems are taken out of the textbook, your textbook, the Zumdahl textbook. And you look at these and try to work through them and, answer the questions the best you can. And you can click your responses, and then you can get out of here. You can just go to the bottom here. And as long as you don't submit the quiz, then it won't count as one of your chances. Now, if I try to submit this quiz, it's going to say, wait a second here, you have 25 unanswered quizzes. Are you sure you want to submit it anyway? And I'm like, oh no, I made a mistake. I don't want to submit it. So I just get out of there. And then I could come back later and it'll open up the quiz. It'll even have my responses, and I can change them if I want. If I didn't like the response, say I talked to a classmate, we were getting together, we went over some stuff, and we decided that that was a good distractor, but it's the wrong answer. So I want to change it. So I can change it. As long as I don't submit it, it doesn't count as one of the chances. Any questions on that? Okay. So there is a homework connected with each one of the chapters, usually. We come all the way down to the end. And that's pretty much what's going to go into your homework grade, your grades for those. All right, if there's no questions, then let's take a look at the syllabus. Okay. Make that a little bigger. So here we have all the course material that we need. This class starts today, January 31st, ends May 28th. My office is MS Math and Science 415M, so it's on the 4th floor. Email me if you need to make an appointment, either in person or if you want to have a Zoom office hour. So after the first 2 weeks, we can do in-person meetings, and we'll have those meetings in my office, but you're still going to have to email me to set up that meeting. Now, you can email me anytime during the week, and I usually get back pretty quick within 24 hours, definitely on the weekend, not so fast. So try to plan ahead. We have a prerequisite for this class, which you've passed, the Chem 200 and 200 lab, and a co-requisite of 201 lab. Now, I told my lab this morning that if you're taking the lab here at Mesa, then you should try to take a lecture at Mesa because they mesh really well. So I'm going to tell you the same here. If you have a lab at another sister college like Miramar City, then they could be doing other things than your lecture. In our lecture, we start out with kinetics, then we go on equilibrium. At Miramar and Mesa, it might not be that way. So just be aware of that. And if you can fit it into your schedule, I recommend taking both the lecture and the lab at the same college. All right, so the rest of the syllabus is the normal attendance withdrawal stuff, which you can read through. There's a little blurb of what we're going to cover, how it kind of connects to Chem 200, where we use that as a basis. And you may need to go back to some of the definitions that you learned in Chem 200. But essentially, this is what I suggest to be successful in this class, and that is try not to fall behind, and in fact, if you can, stay ahead. Use the PowerPoints and our discussions to think about the topics and tighten up your understanding of those concepts. If you don't understand something, then it's nice to have that PowerPoint to kind of zone in on what you don't understand. So when we go over it in our discussion, you can ask questions. And that's either in Zoom or in 2 weeks when we meet in person. So we'll be using our time together in our discussion / lecture, whatever you want to call it, as also a study session. So in those so-called lectures, we can go over any homework problems that you have. We can go over any problems in lab. We can go over anything in chemistry in those points. And usually I find ample time to do that, as well as to discuss the concepts that you need to know for the course. All right, so it's good to be prepared for those class meetings with your questions. Also, do your homework in advance of the exams, up to 2 weeks if possible. Let's see, some things that you'll need for the class. And like I said, you guys, if you have any questions, please just, blurt it out and stop me from talking. I don't mind.
I had a quick question, Professor.
Yeah, sure.
So I just noticed that I was supposed to be part of the Zoom for your lab. Is it going to be the same time every Monday, Wednesday for the lab?
Yeah, so I have 3 labs. So you missed the morning lab, which meets on Monday, Wednesday at 9:35. I also have an afternoon lab that meets on Monday, Wednesday at 2:20, I believe.
Okay.
Okay, and I also have a Friday lab that meets at 9. Now the Friday lab's a double lab, so that meets for 6 hours 1 time a week, whereas my Monday, Wednesday labs meet twice a week for 3 hours each.
Gotcha.
Okay, now if you missed that one this morning, no problem. I am uploading a Zoom video that we taped from this morning, and that should be processed and ready for you to view. It might even be ready now.
Perfect. Thank you.
Yeah, sure. So you just need to go into that lab course content and look for that Zoom video from the morning session.
Will do.
Awesome. All right. Any other questions? Okay, good. So what are you going to need for this course? You're going to need a college level chemistry textbook. Now, our college picked ZoomDall. And so that's, if you took Chem 200 here, that's the textbook that you used. And that's the one that we'll use. The latest edition is 10th edition, but you can use any earlier edition.
Oh, so if we already had the Zoom doll for like Chemistry 200, we can just use the same textbook?
It depends if it's the full textbook, yes. So it includes those later chapters like chapter 12, kinetics, 13, equilibrium. I know that sometimes they sell volumes of a textbook for the first semester and second semester. So if it's the full year Zoom doll, then yes, you can use it. Now, having said that, you can use any standard general chemistry textbook that's up to a level of college. And there's a lot of good ones out there. Silberberg was one that we used for a long time. Brown LeMay, Yang was another one. Tro. There's a bunch of pretty decent ones. So if you want to use another textbook for these type of topics, then let me know and I'll clear it with me and I'll take a look. Especially when we get back together in 2 weeks, I can look through it and make sure that it's up to snuff, because you'll be just using it mostly for references, looking up definitions and getting a little more info on the concepts.
Has anyone in your previous classes used the digital copy? I'm seeing that there's one available through Mesa Bookstore.
Yeah, I'm sure that they have, but I don't have any feedback on it. It's like $30 or something for the digital copy. I think I saw somewhere. So it's significantly cheaper. And I think that should work. I don't see why it wouldn't. If you are taking more courses in chemistry, I would recommend that you get a reference general chem textbook, because chances are you're going to need to look up some stuff for more advanced courses. But if not, then I would go with the electronic copy that I think it's not like a lifetime copy. So it does go away in time, doesn't it?
Yeah, some do. I've done it for previous classes.
Yeah, right. So that's the problem with that. That's why it's cheap. But on the other hand, I mean, you can pick up older editions for a lot less than the current ones. At least I know that used to be true. I'm not sure if that's still true these days. So thanks for that question. All right, so you're going to need a general chemistry textbook that's college level. You're going to need a scientific calculator, and you're going to need to know how to use it. So it's not going to do you much good if you can't use it. And the only way to learn how to use it, I think, is to practice doing it with problems, bring it into lecture. Chances are, if I don't know how to use your calculator, somebody will be there that can help us figure it out. And it like I said in my lab, it doesn't have to be an expensive endeavor. It can be something like $10 to $20. I use an old Texas Instrument 30X. It's pretty basic, and I think it was $10 10 or 20 years ago when I bought it. So, all righty, and you're going to need access, which I assume you already have, to the Canvas course content so you can do your homework and such. All right. What else do we have here? A little blurb on your final, the homework and your quizzes, how they go into your grade. 10% for those homework is going to go into your grade. 70% for 3 exams, and the finals worth 20%. So the equation for the overall grade is weighted. So you have 70% of your overall grade comes from your average exam grades, and that's the 3 exams, exam 1, 2, and 3. Exam 1 covers kinetics, that's chapter 12 in the Zumdahl, and equilibrium, which is chapter 13 in the Zumdahl. The second exam covers these chapters and so forth. Okay. The final, which is going to be cumulative and online, multiple choice over like 3 or 4 days. So there's going to be about 100 questions for the final, but it's going to be more of a capstone kind of adventure where you get to use your textbook or anything that you want.
Wait, we
And
have multiple days to do the final?
yes. Now, the purpose of this is not only to help you boost your grade, but also give you an appreciation of all the things that you've learned throughout this semester. So not only will it cover the final, those latter chapters that weren't on the 3 previous exams, it'll have questions from all the chapters that we go over. So I like it because it gives you an opportunity to maybe make connections between concepts from one chapter to another. And it's not at high pressure during that finals week, because you're going to have a lot of time to do it, I think, if you don't procrastinate.
Hi, Professor, I have a question.
Yeah.
Does the final exam include questions from Gen Chem 1?
Only in the respect that they use concepts from that, but not any specific questions from that. So, for example, I'm not going to ask you to tell which material is homogeneous and heterogeneous, but I might ask you questions on calculating a concentration based off of mixing 2 chemicals of different kinds. So a dilution type problem. So those kind of problems are embedded in things that we do in Chem 201. So you have to know those 200 concepts, but it's not going to be anything like pulled from a chapter in the first semester. Do you know what I'm kind of saying?
Yeah, understood. Thanks.
Okay. Yeah, because there's a lot of foundation material that you have to remember from Chem 200 to be successful in Chem 201. But I'm not going to test you on that directly. It's always going to be indirectly, because you have to know that to do the 201 stuff. All righty. Okay, so in summary, your grade is going to be based off of these parts. 10% of your grade is those homeworks, which you can do twice to get the highest grade possible. 20% from that final, and then the bulk of your grade is going to be on those 3 exams. Okay, the breakdown for A's and B's is the usual scale. All right, now how to read our schedule. So today's the 31st. Here's our week 1. We meet on Monday and Wednesday in week 1. So this is what we're going to discuss. Oh, that time is wrong. I got to change that. It's 12:45 is when we start, not 9:35. So that's a typo. But anyway, we're going to talk about kinetics in a little bit. And that kinetics homework is due Sunday night on February 13th at 11:59 at night. So it's the last possible second of that day. You have to submit that homework. Now, remember I was saying that's kind of these due dates are not real due dates. They're just there to keep you up to pace. So if you miss it, it's okay. You can go back and still do it. And if it doesn't grade it and give you the grade, then just tell me and I'll force it to do that. But try to stay up to snuff. Don't fall behind, because these are going to help you in the exams. So notice that this week we're going to talk about kinetics on Monday and Wednesday. Then next week, again, we're going to talk about kinetics on Monday and Wednesday. It will be our last day, and that's why this homework isn't due until Sunday night, the day before we meet again on Monday to talk about different material, which is equilibrium. So hopefully you'll have a pretty good understanding of what's going on in kinetics before you get to the chapter in equilibrium, or before we start discussing it. And then for equilibrium, it's only going to take us 2 discussion meetings, and those meetings are going to be in person, because we're going to meet in person in our class at 12:45. So I have to change that. Remember, that's wrong. And I believe it's MS 411 or 414 is our lecture hall. Let me look that up real
It's
quick.
411.
Oh, thank you. Thank you for checking that. So I want to not get that wrong. So 411 at 12:45. Yeah, there it is. I got it written down too. On February 14th, Valentine's Day, we're going to be talking about equilibrium and anything else you want, really. These are times we get together and go over any problems. If there's no problems, then I just hash through that material that we plan for the day. Now we're going to finish that off that first week. So that's why this homework is due Sunday night before we start the next material, which is acid bases. We have a holiday on that Monday. And then on Wednesday, we start the acids and bases chapter. So this due date isn't a Sunday. It's a Tuesday night, I think. Right, because Monday's the 21st, but we don't meet, it's a holiday. So I pushed that homework back to Tuesday night, the 22nd, and then we meet. So you really want to try to get ahead and see if you have any problems with the homework, so you can ask in our lecture and so forth. So our first exam is on Monday, the 28th of February. And then Wednesday, we will continue our discussion on acids and bases. And then Monday, March 7th, we're going to talk about acid-base equilibrium, the next chapter. And we're going to talk about that on Wednesday too. And then we go to complex ions. That's the next chapter, 16. We're going to finish 15 and go on to 16. Next week, we start thermo. Then there's spring break. Then we come back from spring break on Monday, April 4th. Questions and answers on anything. If not, we're going to go on and talk about thermo. If you have questions, or maybe we'll go over one of those back tests, the first one, or sorry, the second one. And then on Wednesday, we're going to have exam 2. of week 9. And so forth. So I think you can follow that schedule all the way to the end. So here's our that finals week. I think I'll release that final Monday morning. It'll give you a chance to take a peek at it to see if you have any questions on the questions. So when we meet on Monday at 12:45 in the afternoon, you can ask questions on the final that's posted, and it's not going to be due for 4 days later. And it's multiple choice. All righty. And that's the end of the important stuff, I think, in our syllabus and schedule.
Are all of the exams going to be multiple choice?
Nope,
Okay, just the final.
just the final. Those other 3, like the example that I have here. Let's go back to home. I have these back tests. Here's an example of exam 1 that we looked at. Here's an example of exam 2, an example of exam 3. Each one of these exams are about 4 pages, and they're problem. So you come to class, you write out the problems, so I can assign partial credit when I grade them to see what you have learned. Any questions on that?
Yep, Professor, I have a question about the schedule.
Uh-huh.
So May 23rd would be our last actual in-person lecture.
Yeah. Let's
Great,
check that.
thanks.
Yeah, let's check that out. I have it popped up again. Let's go to this. Yeah, so May 23rd, Monday. Yes. So that's our last gathering. We can talk about any of the problems that you have with the final. And what I usually do in that session, if there's any questions, is I just go over that problem and try to clarify it and help you answer the question, but I don't give you the answer. Okay. All right, any other questions about the schedule or syllabus?
I don't think so.
Okay. All righty. So I think that's it then. Any questions about any of the content that's provided in Canvas?
Don't think so.
Is there a new Zoom link for the lab? Or is it the same?
It's the same. It's the
Okay.
same Zoom room, yeah. Okay. All right, so if there's no questions, let's see. It's 1:26. This class goes to about 2:10 or so. So I just want to go over some of the introductory material in kinetics. So you would go to follow these notes, you would go to these PDF files in your Canvas, and you can download them and so forth. But I'm gonna just open that file because I have it here on reaction kinetics. And now we can talk about our first chapter, yay, in Chem 201, unless there's an objection. Anybody have any objections about going over this?
Got a quick question.
Yeah, go ahead.
If it's been
like over a year since Chem 200. Are there any specific topics you recommend brushing up on, or just kind of all of it?
Yeah, kind of all of it, but nothing specific. I'd like to take this question and tell students to refresh your Chem 200 on a need-to-know basis. So if you're going through a problem or you're looking at something in Chem 201 and it says something about molality, and you're like, oh, I know it's like molarity, but it's something different. So I'm going to need to know that definition. So you go back in your Chem 200, or if you have that textbook for the whole year, not just a semester, then you can look that up from your stuff from Chem 200.
Thank you.
Yeah. So when in doubt, if you're reading something from Chem 201 and you don't understand it, then if it's a definition, by all means, look it up and understand it in the context of Chem 200. And then you can use that as a foundation for adding stuff to from 201. All right. Any other questions? Okay, so I have a question for you guys. Reaction kinetics. Have you studied this before in Chem 200?
Not, I mean, we've studied reactions, but not really the rate so much.
Right, so you haven't. And
I mean, like, it's probably been touched on. I mean, not like even in specifically saying, but like the related like concepts have probably been like touched on a little bit, but not like the concept itself.
yeah, yep. Maybe in passing or just mentioned, but kinetics is kind of a completely new topic for you guys so far in your chemistry career. And that's going to be what it is for the whole 201 experience. Unlike Chem 200, where the stuff that you did in Chem 200 was very similar to things that you did in the prerequisite course 152. So with Chem 201, it's going to be pretty much all new. So I think most of you are going to have to put in a lot more time in understanding what's going on in Chem 201 than you did in Chem 200. It's not just a rehash. It's using the foundations that you had and building on them. Okay, so having said that, what is kinetics? What is reaction kinetics? And you did answer that, which is it's related to the speed of reactions. Well, you've studied reactions and you've studied all different kinds of reactions in Chem 200. Can anybody name a particular category of Chem 200 reactions?
Combustion reaction?
Yeah, combustions. And how do you feel about the speed of combustion reactions relative to other types?
Probably faster.
Mm-hmm. Sure, they're explosive. So they're going to be one of the fastest, right? What other reactions do you remember?
Acid-base reactions.
Awesome.
Double displacement?
Yeah, double displacement, single displacement, rearrangement. What else?
I don't think rearrangement was a type of reaction.
Oh, okay. So maybe that's more towards an organic. Now, rearrangement reactions, you may.
Well, yeah, it's fairly obvious like what it would be, but like there was like a list of like 8 different reactions or whatever. And
yeah,
then,
that you went over. So maybe rearrangement wasn't one of them.
yeah.
Let's see if I could think of another Chem 200 that you might have. How about radical reactions? Did you look at those in Chem 200?
No.
No radical reactions. Okay, well, there's a whole bunch of different categories for types of reactions. And of course, we don't look at all of them, but let's just let it suffice to say that we look at an example number of them and apply concepts to them that would be appropriate for any reaction type. All right, so the first thing that we want to talk about is, well, chemical kinetics, the speed of reactions. And this first topic here is really what we've been talking about. What kind of reaction is it? Is it an acid-base reaction? Is it a combustion? Is it a displacement or an exchange reaction? That's what you guys called it, Chem 200. Single and double exchange, and so forth. So that's something to consider important for understanding the kinetics, but we're not going to model that or talk too much besides just mentioning, okay, well, that's a certain category of reactions, and that may have drastically different rates than others. But other things that affect the reaction rate besides that are named here. For example, the concentration of a reactant will affect the rate, the temperature, the action of a catalyst, surface area, and so much more. So ... there's other factors. But these are representative. And if we can understand how these factors affect the rates of chemical reactions, then in theory, we can look at anything. So if you go someday and do research at a university, you'll be able to apply these techniques to maybe something else that affects chemical reactions. But the things that we're going to look at in specific are these guys right here, 2 through 4. We're going to look at these effects, and we're going to try to mathematically model . So what do I mean by that? Mathematically model these effects. Does anybody know?
To create an equation where we could calculate the speed of the reaction based on some of these factors.
Awesome. That's exactly it. So we want to look at possible mathematical equations that can be used to model these effects. And when I say model, I mean it's going to reflect experimental data that has been taken, but also experimental data that could be taken in the future. So not only will it model data that you have at hand, but it can be used as a mathematical equation to predict what the data would look like in the future. So that you can see that that's a pretty powerful way to look at chemical concepts. And that's why math is so important in chemistry, as well as physics and biology. Now, this last one, surface area, is a physical state. And we don't get into the details of how surface area affects reaction rate. But I think you have a pretty good idea of what that effect would be. So if I increase the surface area of the reactants that are coming together to react, what do you think is going to happen to the rate?
It'll increase.
Yeah, right. So if I increase the surface area, I expect an increase in the rate. And this is true. You can look up online maybe let's see. I think you can look up this Dragon's Breath demo. And you'll find that there's these demonstrations which show this effect really nicely. But I'm not going to do it here. The ones that we're going to do, like I said, is number 2, 3, and 4. We're going to look at these in a little more detail. And I think in general, you can pick out what the effect would be for each one of these. For example, for number 2, if I increase the concentration of a reactant, what happens to the rate?
Increases.
Awesome. How about temperature?
That would depend on what temperature it reacts best at.
Okay, well, they all depend on a lot of things, but in general, the reaction rate increases when you increase concentration, but not always. For example, you can imagine adding.
Oh, I thought you said temperature.
I did. I did, but I'm going back because
Oh,
it's the
okay.
same with temperature. We said that reactant concentration, when it increases the rate. And in general, it does, but not always. You can imagine adding a retardant to a reaction like they do for chain reactions in nuclear energy. You know, if you don't get a hold of that chain reaction, you can have a meltdown and a lot of problems. So you have to add in these boron control rods. So you increase the concentration of boron and it slows the reaction down. So it's not always that increase of concentration increases the rate, but in general, it does. Okay, now in general, when I increase the temperature, what happens to the rate?
It increases.
Go up.
Yes, in general, it does, but not always. So you were right to say it depends. And it depends on all of these. And that's what makes chemistry so interesting, and it also makes it hard for a lot of people, because the answers many times to questions, the answer is it depends. It depends on the details, and so you have to learn the details. And now the action of a catalyst, this one is not like the first two. If I increase the concentration of a catalyst, what does it do to the rate?
Would increase the rate.
Yeah, always, right? So a catalyst always increases the rate. All right, so we're gonna go into these in more detail. We're just taking a look at, you know, what are some of the factors that can affect a reaction rate. Also, we should probably kind of think about reaction rates as connected to a reaction. So when I say I want to talk about the rate of a reaction of some A going to B, what does that mean? What does it mean to talk about rates of A going to B?
The rate at which A is converted to B, or basically reactants are converted to product.
Right. Now, how do I measure something like that? Because I can measure my rate of speed if I ran across the classroom or something like that, right? What would my units be for the rate of speed of me running?
Let's see, like feet per second or something.
Yep, exactly. Now, what would it be for the rate of a reaction?
It would be the concentration of reactants versus the concentration of products over time.
Okay, maybe that's a possible solution, but the way that we do it is we do it one or the other. So we look at the rate of consumption of A over time, or the rate of production of B over time. Okay, and the units that you can use for something like this is shown here in this equation, where I have a delta, that's the Greek symbol for delta, moles of B over delta T. What does delta mean?
Change over time.
Yeah, specifically the final minus the initial. So delta moles would be the final moles of B minus the initial moles of B over the change of time that number of moles changed. Does that make sense? Any questions on this equation here?
No.
No questions? Okay, so we have a delta number of moles of B over delta T. When I take that ratio, I get units of moles per time, right? Or, in seconds, if you will, moles per second. Whereas a rate of me running a class across the classroom could have been feet per second. So it's what I'm trying to do here is to connect an equation, a mathematical equation that deals with reactions, right? With reactions to something that you already know, somebody running on a track or something, or a car, miles per hour. So you see that the units make sense. So this ratio, this first ratio, corresponds to the rate of production of B, moles per second. The second ratio, right here, this guy, what kind of a rate does that correspond to? Anybody? The rate of
Decrease.
the rate, yes, the rate of decrease, or the rate of consumption of A. That's what that is. And the units for this would be moles of A per second. Okay, now these guys are related. They're related to each other because for each mole of A that I use, I create 1 mole of B. So as this is increasing in time, this is decreasing in time because of the final minus initial, which is why I have to put a negative sign out here if I'm going to make them equal. All right. So this goes up in time, and this goes down the same amount in time. And so that's the same number, except it's a change in the sign. And that's just because of the way we define the deltas. The deltas are always final minus initial. So 1 goes up, so the final is greater than the initial. 1 goes down, so the final is less than the initial. So you get a negative value for that case out here. But in any case, I think you can see how rates, something that you're used to talking about for, somebody's speed in a track or a car, transfers to a chemical reaction. Any questions on that? All right, good. So for chemical reactions, we're talking about moles per second. And here's an example of a reaction from A going to B. This time we're taking a look at the number of moles and how they change in time. So you see we start out with 0 B, and here it says we start out with 1 mole of A. So as the reaction starts, there isn't any B. So it's 0, 1 mole of A. And then as we decrease the moles of A by 0.24, we increase the moles of B by 0.24. So A went down by that increment, that change, and B went up by that same change. Okay. So in our rate equals, for this first point right here, we would have the change in B over change in time. Right, that's what that equals. That equals minus the change in A over the change in time, which for that first point would be 0.24 over that time period, which is about 10 seconds, if you look here. And that should equal a negative minus 0.24 over 10 for A, because A went down. So its final minus initial would be 0.76 minus 1, which is minus 0.24. Okay. So any questions on that equation and how it relates to that plot? So we're good. So we see how the rate of consumption of A is related to the rate of production of B. Okay, good. No questions? All right. Well, you can fill in these blanks here. And then if you have a question, then when we meet in a couple of weeks or next time, you can ask. We can go over that again. But I'm going to skip right to some data on rates. Now, for chemical reactions, when we go to the lab, we don't usually measure directly in moles. We measure concentrations and see how concentration changes. So instead of using that equation that we just introduced for rate, we use a similar equation, except that that equation for rate talks about the change in the concentration. So it's delta change in the concentration of, say, A over delta T, and not moles. But that doesn't add any more complexity to the previous equation. It just adds in a constant, right? Remember, concentration from Chem 200, what's the units of concentration, or what is a unit of concentration? Give you a hint.
Molarity.
Yeah. And so molarity is moles per liter. And that other equation that we just looked at was moles. So we just added in this volume, which for any experiment that we do in Chem 201, that volume's not going to change. Whatever we have mixed in that beaker, the volume is what it is. The volume stays the same. So we just introduced a constant volume. So that doesn't change any of the mathematical functions that we're going to look at. It just adds in a constant for volume. All right. Now, here's our time. This is some experimental data. We have time, and we see how the concentration of one of our reactants here for this reaction changes in time. What happens to the concentration as time goes on?
It goes down.
Yeah, of course, it goes down because it's a reactant. So it's decreasing. So at any one of these intervals, for this first interval from 0 to 100 seconds, I could take the change in the concentration, which is final minus initial, 0.0904 minus 0.1, and I divide that by the time, which is 100 seconds, and I get this average rate for that period of time. All right. And I took that negative sign away because this is going to be negative, but a negative times a negative, that negative decreases, and it makes all these positive. So we talk about positive rates. It's just that we're saying this is the rate of consumption. So it's understood that that negative canceled out. And also notice now, instead of having moles per second, we have units of molarities per second. But that shouldn't be a big deal. It's just you have that extra constant of volume in there to make the conversion. It doesn't change any of the ideas of rate. Okay, any questions with that? All righty. Let's take a look at a plot of concentration versus time for that reaction, just to get another look at this concept of rate. So I have concentration here on the y-axis and time on the x. And I can see again how those concentrations change in time. They decrease. Okay. And if I go back, I see what happens to the rate as time goes on. Anybody?
It's going down.
Yeah, it decreases. Does anybody know why it decreases? The rate decreases because
There's less reactants.
yeah, the concentration's decreasing. So it all makes sense. The concentration decreases, the rate decreases. Why? Because that's the rate formula. When you put it in the rate formula, this mathematical formula, it shows that trend and it all makes sense, right? There's the data. There's the concentration decreasing. Here's the rate decreasing. And it makes sense because we define the rate that way. All right. So I see concentration in time on this plot, but I don't see rate. How do I take this data and convert it to rate data? Well, since this class is a non-calculus based class, we can't use calculus to take the derivative of this curve and analyze it at any point in time to find rate. But we don't have to because there's another way to get at rate. Now, again, what's the units of rate for reactions?
Number of reactants
Yep.
over time.
Right. Okay, good. So, and we measure the number of reactants in terms of moles, but we don't want to use moles because in the laboratory, it's more comfortable to use molarity and add in that volume. So it's molarity per time. Oftentimes it's seconds. And in this case, it will be seconds. So I need a value that has molarity in the numerator and seconds in the denominator. And I have molarity as a y-axis and time as x. So what quantity in this plot is going to be related to rate? Molarity per second.
Slope.
Yes, y over x, right? The slope. The slope. Remember, that equals change in y over the change in x, which in this picture is the change in the concentration of, well, reactant A, the C4H9 Br, over the change in x, which is the change in time. And so all I would need to do is to put in a negative sign, and then it equals our equation for rate of consumption of A. Okay, so how do I get at that? Well, you probably have done this before in math classes. To find the slope of a line at a point, that's called, the instantaneous slope or instantaneous rate in this context. That would be the rate at some point in time. And so what is done when you have a curve is you draw a tangent. This is the tangent to the curve at that time of interest, 0. So the tangent just touches the curve at that one point. And then once I have that tangent, all I need to do is find the slope or the change in the y-axis of that tangent. And that gives me the rate at that point in time of interest. So I think you guys have done this in your math classes before. You've done something like this. And so you don't need calculus, right? And you can see that the slope here in the beginning of the reaction is what compared to the slope of the tangent towards the end?
It's steeper.
Yeah, so the slope gets smaller, indicating the rate is getting smaller. And that's what we found back here previously. The rate gets smaller here. And it makes sense mathematically with our formulas. Okay. So any questions on this? So we're just taking a look at this concept in pictures and in formulas and trying to connect it to what we already know as far as, running on a track or reactions from Chem 200. So we're kind of just dipping our toe into this world where we kind of have an idea of what's going on, and we're trying to apply some of the concepts that we should be comfortable with to an area that we're not so comfortable with, which is chemical reactions. Any questions so far? All righty, so we're going to just keep on going then. Here we have that reaction again. Take a look at this reaction. We define our rate using the definition of rate for a chemical reaction as equal to minus the change in the concentration of a reactant, in this case C4H9Br, over the change in time. And that is related to the rate of production of a product. Okay. Now, do you remember why there's a negative sign here and not here?
One of them is being consumed, the other one's being produced.
Brilliant. That's it. Okay. So we just have to put that negative because of the way delta is defined as final minus initial. So you get a negative for that numerator in this part, but here, since it's being produced, it's going to be positive. And it's going to be the same amount. Why is it going to be the same amount? Does anybody know?
because of like the law of conservation of mass or whatever?
Well, it's even easier than that. It's because of Chem 200 and the stoichiometric coefficients. They're one to one. For every one of these I use, I have to produce one of those. Right?
Yeah.
Yeah, that's what your Chem 200 told you. And that's why. So that leads to the question of what do we do when it's not one-to-one, but when we have stoichiometric coefficients that are different. So here I have a generic reaction with generic stoichiometric coefficients. So this is reactant A with stoichiometric coefficient of A. So I have AAs react with BBs to make CCs plus DDs. And here is the general rate equation that relates all those rates. So this says that the rate, and this rate is the rate of the overall reaction. That's what we've defined. This rate is the rate of the overall reaction equals minus 1 over A, the stoichiometric coefficient, times this ratio, which we now know is the rate of consumption of A, right? Does anybody know what this ratio right here equals?
Rate of production of B? Wait, no. Wait, yeah. No. Hold on. Rate of production of, wait, rate of consumption of B.
Yes, you nailed it. How about this one?
Rate of production of C.
Yeah. So these are rates of production over here of C, and this would be the rate of production of D. So in a problem, if they tell you that, I don't know, the rate of production of HBr from some experiment is 10 molarities per second, then I can calculate the rate of the overall reaction by using its stoichiometric coefficient right there. Furthermore, if I'm given this rate of production of, say, 10 molarities per second of HBr, I can calculate the rate of production of this other product, or I can calculate the rate of consumption of anything else in that reaction. I can calculate all these just using their stoichiometric coefficients. Okay, any questions on that?
No.
Awesome. So next time, I want to stop there, but next time we're going to go back to this equation and we're going to try an example or two in applying this when we have stoichiometric coefficients. And so then it will allow you to relate the rate of the overall reaction to the rate of consumption of any of the reactants or the rate of production of any of the products by using those stoichiometric coefficients. And so we'll go back to that on Wednesday, pick up from there. I'm going to break a little early, like 3 minutes, I think, in case you guys have any questions. Okay. Any
It's the
questions?
same Zoom room for the lab meeting in a bit, correct?
Yeah, so you get into the lab meeting, you go to your lab canvas, and in there, there's a link to this same Zoom room.
Got it.
Got it. Okay. Alrighty. So I'm just going to hang out here. If anybody has any questions, fire away. I'm going to probably stop recording now. Oops.
All right, thank you, Professor.
Yep. Thank you, guys.
Thank you.
Thank you.
Thank you.